Welcome to Earth Science, everybody. How we doing? So let's talk review on the energy units. Now it's December 7th. If you were here on that Wednesday, you did this. If you were not here, you're going to want to do this before the test on Friday to make sure we get all the ideas about this unit onto one piece of paper. So that's where we're at. So this graphic's not perfect because it shows these at equal wavelengths. We'll go towards the bottom of this and talk about how those are not equal wavelengths. But it kind of looked cool to me this morning when I grabbed it, so I said, hey, let's use it. This unit is all about energy coming out of the sun and hitting the Earth and what those interactions are with our surface. And then as the Earth then gives its energy back out to space, where it would technically be a different wavelength. It's really that. That's the reason we have weather at the end of the day. Radiation from the sun heats our planet, but our planet is varied. First off, it's round. It's got a curved surface, so it hits at different angles in different places at different latitudes. It's made of different stuff. Some of it's land, some of it's water. The part that's land, some of it is like white snow caps, some of it's sand like deserts, some of it's forests. It's all kinds of different, right? And different surfaces heats at different rates. And what that means is that every day this is happening as the Earth spins and gives us day and night, this radiation hitting us, heating different surfaces differently, leads to differences in our atmosphere. And nature likes to fix differences. It doesn't like when there's an imbalance. So like we've done the sand and water thing to death, right? If it gets hot over the sand but cooler over the water during the day, there's a difference. That hotter air will have a different density than the cooler air. And then nature wants to fix that. So it makes the air move, right? Makes the air move is kind of like personifying it. That's not technically how it works. But the point is that nature likes to fix these imbalances. And it does that by moving the air, which we call wind and really like we call weather. That's how weather works, because the air in one place moves to another place. So if you stepped out this morning and said, geez, it feels a little bit warm for this time of year, it's because the air moved here from somewhere else that is warm. And then maybe a couple days down the road, it's colder. And you say, geez, it's cold this morning. Well, that's because the air moved here from some place that's cold, right? That's it. Moving air because of this imbalance in energy caused by the Earth heating differently. That's what we're working on for the next 6 weeks, right? Through the end of the marking period. So some of those differences, we went through these to say, you did this lab, and if you've really done this lab by wearing a dark shirt out on a sunny day, if you've done that, you know that dark colors heat and cools faster. Yeah. What if we talk about texture? We didn't really talk about this a ton, but if we compared a smooth surface to a rough surface, I'll use Cami here to zoom in. If you compare these, the rough surface has more, it's a thing we call surface area. It has more available surface to interact with that source of heat. It's like a longer line. It's just crunched into a smaller amount of space with all the little nooks and crannies that it has. That allows it to grab energy more efficiently. And it also like, it shows this radiation kind of bouncing around as it reflects, right? But it also like, if this radiates some heat out, it can hit another part, so it can kind of radiate unto itself because of these little rough surfaces that it has. So those also, compared to smooth surfaces, rough heats and cools faster. How about land versus water? We did a whole lot of that. The lab where you had a beaker of sand in front of the lamp and a beaker of water in front of the lamp were to show us that land heats and cools faster. And really, as part of that, an important part of that, this is almost like writing the same thing again, but not quite. An important part of that idea is that water holds heat well. Once water warms up, it holds onto that heat really well. It doesn't let it go too easily. It takes a lot of energy to get it to warm up, but once it warms up, it stays warm. Now, we've observed this. You've observed this. And in fact, you're going to have a question here in not too long talking about, hey, what about in wintertime? Why would Watertown be warmer on average than it is in Old Forge? Well, it's because of this water thing. Water cools down very slowly. So it spent all summer getting warmer and warmer and warmer in the sun. This is a huge amount of water, 700 feet deep, 800 feet deep. Spent all summer very slowly getting warmer. And then all of a sudden, like that, when it gets to winter, it can go from warm to sub-freezing in like a week. You guys have all experienced that. It can even happen in a day. All of a sudden, the land freezes, but the water does not. The water holds on to its heat. So Watertown, being close to the water, will benefit from the heat that's like in that water. It will keep Watertown a little bit warmer, whereas Old Forge, being far away from the water, does not get that benefit of staying warm from the lake and will cool down much faster. All right. It's like the reason why houses can use water as a method of heating. If you've got baseboard hot water heats, those long things that go along the floor, some of those are electric, but some of them have hot water pipes that literally go into them and come back out the other side and just run through. It's hot water that slowly radiates its heat out into the room. If water didn't hold onto its heat well, you would heat it in a boiler in the basement. It would make it like halfway to your heater or to your shower. It would lose all of its heat, and you would never have a warm shower, right? But it does. It holds its heat really well in your shower and in Lake Ontario, right? And that has to do with the specific heats. So this was likely a new vocab word for everybody when it was the beginning of the unit here. What does specific heat mean? I look at the label to figure out the definition here. How many joules? So maybe that's a new one on you. Joules is a unit of energy. How much energy does it take to make a gram of something go up by a degree Celsius? Those are the numbers that answer that question. How much energy does it take to get a gram of something to go up by a degree Celsius? So water takes 4.18 joules of energy to get a gram of it to go up by a degree C. Lead only takes 0.13. That's a huge difference. So this has a very high specific heat. It has a very low specific heat. What that means, same thing, I know you're probably getting sick of writing this, we've said it multiple times, is that this heats and cools slowly. Whereas this lead would heat and cool quickly. It only takes a tenth of a joule to make a gram of lead go up by a degree C, whereas it takes 4 1/10 to make water go up by that much. Huge difference. Yeah? All right, cool. This property is a water ESRT. We haven't looked at a ton, but it really has been pretty minimized in the modern version of our regents here in Nurse Science. So what I'm going to promise you, and I'm going to show you a question that deals with this. Circle these with me right now, if you would. Gained, released, gained, released. When this happens, it's either melting, freezing, vaporization, or condensation. When this happens, energy has to be either gained or released by the water itself, right? If I have an ice cube and I want to melt it in my hand, the ice cube is going to gain energy from my hand in order to melt, and it needs that much. Now, don't panic here. Don't worry about the numbers. Don't say, oh man, these look like a lot of vocab words. These questions are very easy. Just like you circle those for me. So we've here's all 4 choices that could possibly be an answer. Either it gains 334, or it releases 334, or it gains 2260, or it releases 2260. That's it. They won't make you do any numbers. They won't even make you compare them. It'll just be during melting, it gains 334. During freezing, it releases 334. During vaporization, which is like boiling, evaporation, it gains 2260. During condensation, which is going from a gas to a liquid, it releases 2260. That might be a bit more of a thing when we talk about cloud formation and stuff like that. But for today, again, let's look at a question to see what they ask here, and you'll see how easy it is. During the process of condensation, water vapor does what? Use the reference table. I don't expect you to just know that off the top of your head. During condensation, water releases 2260. If that's a choice, then it is that easy. And it is choice 2. During condensation, it releases 2260. Those are the only questions I'm going to give you on this. All right. If we dig a little deeper during clouds, we do. If not, we won't. But that's pretty much all that the reference table, that the regents will do with that reference table anymore. Cool? All right, keeping it moving then. This was like our temperature lag. Nope, this was like our temperature range lab. And what we looked at here was to say, what is it like at this city? And I don't know if it blew up. Versus this city. Where are they located? So in the video for this lab, I said that I lived in Minneapolis for a couple of years where it got ridiculously cold. Also, and I expected that. But it also got really, really hot during the summers. And I don't think I was quite as prepared for that. So this is what it's like when you live, I'm going to say inland, which is going to be far from oceans. If you live near an ocean, the ocean, because, and you're going to find this to be a very repetitive theme here, because water heats and cools slowly is going to be the answer to, like, especially the back page down here. It's going to be the answer to most of those. That's the idea behind this. But the Regents really likes it. That's why we're going to take our time and be deliberate with it. If you live near the ocean, if you're coastal, heat and cool very slowly. Okay. So on this lab, I did have people tell me, oh, blah, 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 this city, blah, blah, blah city is hotter. And that's not a good answer for this lab. If you say it's a hotter city, what are you talking about? Are you talking about summer or are you talking about winter? Because the city that's hotter in summer is colder in winter, and the city that's cooler in summer is warmer in winter. So hot versus cold aren't really very easy to think about. What you'll want to think about is the idea of range. This is all about range. Chuck that down here. Range is the answer to these. So what does that mean? I'm going to do big letters so that we get this down. I'm going to throw an exclamation point there. What range means is what's the difference from our coldest time of year, where the temperatures are like here, to our hottest time of year, where the temperatures are like here. That is your temperature range, that difference. If you live in a coastal area where, because there's so much water there and water takes so much time to heat up and so much time to cool down, you don't get as cold in winter, you don't get as hot in summer, so the range is a lot smaller. That's how you answer the concepts in this lab. It's either a large range city far from the ocean or a small range city close to the ocean. So if we do that as a really quick like relationship in less giant letters, closer, smaller than that. Closer to water equals smaller range. And I'm not talking like a little pond here. This has to be a pretty serious amount of water for this effect to work. If it's a small pond, it just freezes over and doesn't do anything. Like a Great Lake up to an ocean will be where this is the case. Cool. I think this is going to be part of the lab in the future. You guys plotted graphs that look pretty much, should look like this broadly, generally, maybe a little different. What I think I'm going to do next year is put these little graphs on the side to say, okay, how do you figure out that range? Go from high to low. That's a big range. Go from high to low here. That's a small range. Small range goes with coastal cities because water heats and cools slowly, right? This rule will come up and come up and come up. Go back and circle it. And here it is again, sea breeze versus land breeze. This is like during the day, land heats faster than water. So you get rising air here, and then the cooler air sinks here, and you get this convection cell, you get this flow. And if you are a tiny little person, or if you are on a sailboat, you recognize that convection cell and that movement of air as wind. So the breeze blows off the lake in this situation, which we call a sea breeze. Oh, that was weird. Sorry. At night, again, sticking to all the stuff we've talked about, the land's going to cool off more. The water heated up very slowly, but will cool off very slowly. So now this will be cooler. The air sinks there. It's more dense. The air rises over here, and the convection cell flops around. So if you go back to the beach at night, now that the breeze is coming from behind you, we call that a land breeze. And they're real things. This happens. This happens on Lake Ontario. That is right, even though they don't like it. This happens on Lake Ontario. Now, if there's like a major wind system, a big pressure system, a front that's coming through, it's going to wipe this off the map. This only stands a chance without a major synoptic weather system coming through, right? So take a calm summer day without a whole lot of wind. If you go to the lakeshore, you'll experience this, especially when the seasons are like early in the season when the lake is really cold still and the land heats up a lot. That's when it can really go and give you some nice wind along the breeze, even though there's no wind out in the middle of the lake. And I told everybody today we were in a sail race where we experienced this. We had to go from Oswego around this little island and back, and we got stuck right about here with absolutely no wind whatsoever. The sails were just flopped. The people that said, "Hey, I think there's such a thing as sea breeze because I paid attention to air science," rode the shore, took a much longer path, but made it back to Oswego because of the wind being there on the shoreline the whole way. We didn't. Then we lost badly. Anyway, what do you think? That'll do that. Next, these are very straightforward. 3 things got to be in our head to make it. A, B, and C. What are these methods of energy transfer? These are the ways in which energy can move. So maybe I'll write that over here. Forms of energy transfer. Expect diagrams like this to be on the test. I guarantee it. A is when a fluid, either a liquid or a gas, is flowing. So like in your macaroni and cheese pot when it's going, you get these little currents of spinning around, or in the atmosphere in a gas, you get the swirling around. It's called convection. Heat distributes by that fluid moving. Doesn't work with solids. B, conduction. That's what we did with the aluminum bar between the 2 cups. Physical contact, that's molecule to molecule transfer of energy. And C is like when the coals burn down a bit and when the rocks get hot, you can like feel the glow off of a fire. You put your hands up and you can like feel the heat. Is radiation. So if you want like the short term, how do I stick these in my head? I want that bread. How do I stick these in my head? Walk into the door of the test. Convection is a flow. Conduction, the key word is touching. Molecule to molecule contact. And radiation is electromagnetic waves. That's a fancy way of saying it. Let's just chuck waves there, like waves of energy, like the French fry lamp at McDonald's. All right. What do we got? 3 things to go. Thanks for sticking with me. Hit pause if you need a break. We live on a roughly spherical planet, pretty darn spherical. So the sun hits and hits at different angles depending on where you live on that spherical surface. So picture if we just do 2-dimensionally like this piece of paper. There's your round Earth, and whoever is getting hit the most directly is going to get heated the most efficiently. So C, being near the equator, is like this drawing right here. These letters shouldn't be here. They were just from a different document. C is like this. When the sun's coming in directly overhead, that's the most intense it can possibly be when it's shining directly down from overhead. We don't see that in New York. You will never see that in New York. The sun does not go overhead outside of the Tropic of Cancer and the Tropic of Capricorn. And since it's overhead in between those regions throughout the course of the year, it's hot there. It's hot near the equator, right? We know that. Get up towards the mid-latitudes, like where we live, B and D, or maybe a little further that way. That's when you get it at an angle like this. So it's not quite as intense as it is there, but it's not so low that you're not getting much at all. It's the mid-latitudes, and it's the temperate climates that we are all used to. And yes, this angle goes up and down throughout the course of the year. Summer solstice, it's at its highest. Winter solstice, which is coming up, December 21st, it will be at its lowest angle of the year. and that flops back and forth, and that's why we experience different seasons. But broadly, in the mid-latitudes, it's at roughly an angle somewhere right around there. And then get up near the poles, again, depending on the time of year, and it's really coming into a low angle, which means the energy is really spread out per unit area, and it doesn't heat as efficiently, and it's cold, right? So the higher the angle, let's write that as relationship. Higher the angle, the more intense the insolation. Insolation being the fancy pants earth science word for sunlight, incoming solar radiation. Excellent. All right, the greenhouse effect. So if anybody ever gets a greenhouse or a hoop house, if you ever see those, or like it's got like the metal piping as a frame for like a semicircle. You do a bunch of those in a row and then stretch plastic over it for growing plants and extending the growing season. So if you ever get one, I want you to say, I remember my earth science, and I want you to find something that's dark in color and can hold water. So some big, like 5-gallon water jugs, a big rain barrel, something. Paint it black, fill it with water, and remember why that works. That's the other part of it. It's going to be years on the road. You got to remember why it works. It's referred to as either like a heat sink or a thermal mass. So why black? Because dark heats faster. It's going to absorb sunlight more efficiently. Why fill it with water? And you might say, well, geez, water takes a long time to heat up. Wouldn't that be inefficient? It does take a long time to heat up. But once it heats up, it's going to hold on to its heat really well. That thing will stay warm, which is what you want. You want this greenhouse to warm up, right? So then let's just get into the physics of how this works. And we've drawn this. We drew this in the first lesson, lesson A, and we've drawn it in labs. We've considered this many times. And we'll have to continue to consider it as we go through the class. That's the sun. Looks great, doesn't it? So a shorter wavelength of energy comes out of the sun. That wavelength of energy can travel right through glass, no problem. It does that, and it hits things, and those things warm up, which is why you make this something that's great at warming up. If you were to line the floor of this with mirrors, I don't know why you would, but if you were to, the sunlight would hit the mirror, and it would bounce at that same wavelength, go right back out through the glass, and off it goes with no heat transfer. We do this dark so that there is a heat transfer, so that it heats up. And then the big mystery of this whole thing is that things that are warm give off infrared radiation, which is a longer wavelength. And that longer wavelength cannot make it back out through the glass. Infrared radiation gets trapped. That's what a greenhouse is an infrared radiation trapping device, right? So then the big leap is really to say that the Earth and the atmosphere work exactly the same way. Earth, atmosphere, if we've got the sunlight coming in, it does so at a shorter wavelength. It passes right through the atmosphere. Maybe some of it bounces off the tops of clouds or bounces off a snow-covered field or something. But in places, it makes it all the way to the planet, and the planet gets warm. And then when the planet's warm, it gives off infrared radiation, not reflecting, a multi-step process of absorbing, heating up, and then radiating off this energy. With the trick being, just like the glass of the greenhouse, infrared radiation gets trapped. Only it doesn't get trapped by a sheet of plastic or a glass greenhouse. It gets trapped by greenhouse gases. These measurably, very identifiably work the same as the roof of the greenhouse. Greenhouse gases are excellent, are good absorbers of infrared radiation. And we love this. If this weren't a thing, when the planet turns away from the sun, which we call nighttime, all of that energy would just out into space if there were no greenhouse effect. And it would go down by hundreds of degrees. Life probably never would have evolved. It certainly wouldn't have evolved the way it did. Most species aren't capable of handling temperature shifts of multiple hundreds of degrees over the course of a day. So this greenhouse effect is great. When the Earth turns away, we manage to stay warm because the atmosphere holds on to that infrared radiation. Where we got to be careful is if we go too hard on it by putting too many greenhouse gases up in the atmosphere. Those greenhouse gases are, and the regions loves them. So these three are like, put them in the brain. CO2. That's called carbon dioxide. Oh, sorry, screwing this up. CH4, methane. Those are the two that we have control over how much that we are, with our society, opting to put into the atmosphere. At some point, we're going to make better decisions, I think, and come up with better ways to have us have our economy and get around this planet without emitting so much of that. We'll see. The third one is greenhouse gas. The Regents will ask about it, but I tend to stress it less in class because it's water vapor that's in the atmosphere. That's going to be in the atmosphere like it or not, right? We can't really put more or less of that into the atmosphere with any practicality. You could argue that a warmer atmosphere might have more water vapor in it, and therefore it's more efficient, right? But really, these two are the ones that we could exercise control over with some policy. All right, so get those three in your head. No way they're not showing up. On the practice questions, that's exactly what it will look like right there. You'll see it in a few. Once we do one more thing, rate of change problems, I'm very insistent on having them done the same way every time. So we talked about that on 3 separate labs. Here's exactly what they got to look like. Here are all the parts that's got to be there. And now it's time for the test where I promise there will be another one. And I'm promising it's 10 full points. So 10% of the grade is on one of these problems. Just do it exactly the same way every time, and you will make it. This equation right here is available in your Earth Science reference table, so it will be given to you. It'll be on the front page of the lab of the test, or it'll be on some point of the test. Change in value divided by time. So you got to write them out. What is the change in value? What is the time? And that equals your answer. That equals the rate of change. So change in value. Calculate the rate and change from 2000 to 2010 of the average carbon dioxide concentrations in parts per million per year. Let's blow this up a little bit. So in 2000 it was, in 2000 it was at 370. In 2010 it was at 390. So it has changed in that time span by 20. So there's one of the 10 points at least. But 20 what? All the numbers you write down really should have a label with very few exceptions in this course. 20, if I look up here, it says ppm. And even if it's a label you're not really familiar with, that's it. Steal it from the info, it's there. That means parts per million. How many parts per million of the atmosphere? If I hold 1 million air molecules in my hand, that's that many. That's what that means. A little weird maybe, but it's there, right? So that's the change in value is 20 parts per million. There's 2 points. I'll even give a point for throwing the line in there, just like it is in the equation. Divide that by time. From 2000 to 2010, how much time passes? 10 years. There you go. There's 2 more points. The 10 is some point, and the label is a point. Labels, labels, labels. That equals what? So you can grab a calculator. This one I can do in my head, but maybe not always. So you grab a calculator. 20 divided by 10 is 2. And now what's my label? And this is kind of the reason why I bust chops about making sure that we do it, because if you do it correctly, your label is just sitting right there for you for free. You don't need to think at all. I prefer you think, but you don't need to. Parts per million per year. I'm just going to put the slash right here. Okay, parts per million per year, parts per million per year. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 points for those 10 things. All right. That's it. That's how you're going to get your points on this test. All right. Don't throw those away. Those are like, you know exactly what you're going to have to do. Step up and do it. And you can practice one of those right here. There's the numbers and some other practices. So I do recommend you get this done and probably talk to me quick before the test. Try those questions, see how they go. This one's on the hard side and really is more related to what we did last unit. So if that one's a struggle, but you get through the rest, you're probably sitting pretty. Don't forget to check the reference tables. And I did not mention in this review, but we did it yesterday. This question and this question, you need the ocean currents reference table. Don't forget that that's a thing. It's page 4. There's all the answers to those questions just sitting there for free. Those, if you just try to say, oh, geez, I think we talked about the Gulf Stream, maybe it's this, you're wasting points. If you say, oh, the Gulf Stream, that's on page 4 and the answer's sitting there for free, you're going to get your free points. So do it. Use your head. Thanks, everybody. Good luck with the rest.